Dear students, welcome to 24th online class of Control System Engineering. In last chapter, we studied about the root locus and the rules through which we can sketch the root locus. Root locus gave us graphical representation of the path followed by a closed loop system poles when the unknown parameter gain k is varied. We also studied how to achieve desired transient specification by adjusting the gain of closed loop system. Students, now we will start chapter 9, which is design through root locus. Students, by the end of this chapter, you will be able to design a compensator for closed loop system to improve the steady state error with the help of root locus. Also, you will be able to design a controller to improve the transient response of a system. Also, you will study to design a controller which will improve both transient and steady state error with the help of root locus. Dear students, contents of this lecture are Introduction to Controller Design, Ideal Proportional Integral Control, and Lag Compensator. Dear students, root locus gave us a graphical representation of the path followed by closed loop system poles. If we have certain transient design condition, we will find out location of closed loop system poles, and then with the help of gain, we will achieve desired transient specification. As the gain is varied, we move through different region of the response. Setting any value of gain k, we achieve a transient response, which depends on the location of closed loop system poles. Students, with gain adjustment, we are limited to the response that exists along the root locus of closed loop system, which means that if for any set of transient condition, we will find out closed loop system poles if that location of closed loop pole is a part of root locus, we can achieve with the help of gain adjustment. And if that point is not part of root locus, then with gain adjustment we can't achieve that response. Dear students, look at figure A, which represent root locus of a closed loop system. Assume that the desired transient response defined by percent overshoot and settling time is represented by closed loop system pole location B. Unfortunately, on current root locus, specified percent overshoot is achieved by placing the closed loop system poles at point A with the help of simple gain adjustment, where settling time is not the desired one. So our goal is to speed up the response, for which our closed loop system poles required to be at location of B instead of A, at which desired percent overshoot and settling time will be achieved. Now we know that the point B is not the part of root locus, so increase in the speed cannot be accomplished by simple gain adjustment. Dear students, now if you look at figure B, which represents step responses for both pole location A and B, the response shows that for both pole location we have same overshoot, but response due to pole at B is faster compared to poles at location A. Students, one way to solve our problem is to compensate our system with additional poles or zeros. The compensated system has a root locus which will pass through our desired pole location for some value of gain k. It may have disadvantage that compensating system with additional open loop poles and zeros can increase the order of the system, with the subsequent effect on desired response. Dear students, compensators are not only used to improve the transient response, but with this we can also improve steady-state error characteristics independently. Previously, when the gain of the system was adjusted to meet the transient response specification, the steady-state error performance was degraded because both transient response and static error constants are related to the gain. As we increase the gain k to the higher value, the steady-state error will reduce to the smaller value. But with this, our percent overshoot will also increase. On the other hand, reducing the gain will help us to reduce the percent overshoot, but it will also increase the steady-state error. Now, if we use dynamic compensators, these compensating network will allow us to design our system to meet the given transient condition and steady-state error specification simultaneously. Students, now we will study how to improve steady-state error. The compensator which use pure integration for improving the steady-state error or the pure differentiation for the transient response are defined as ideal compensator. Ideal compensators are implemented with the active network, which in case of electric networks require active amplifiers and additional power sources. Dear students, the compensator network which use pure integration or the ideal integral compensator is known as proportional integral controller. Students, on the other hand, those compensator which can be implemented with passive elements such as resistor and capacitor and don't require pure integration or differentiation are not the ideal compensator. The advantage of using passive networks is that they are less expensive and do not require additional power sources for their operation, where their disadvantage is that steady-state error is not driven to the zero, where with ideal compensator we can achieve a zero steady-state error by improving the type of the system. The controller which uses passive networks for improving steady-state error is known as lag compensator or lag controller. Dear students, steady-state error can be improved by placing an open loop pole at origin, because placing a pole at origin in transfer function of open loop system improves the type of the system by 1. For example, if we have type 0 system and if we apply a step input, we will have a finite steady-state error, and for 0 steady-state error we have to improve the system type by 1. Students, if you look at the system in figure A, which consists of a gain k and plant g of s. And from its root locus, it is clear that open loop system have three poles, and the desired operating point is represented by point A. And the forward path system is of type 0 because we have no pole at origin. Here this system is operating with desired transient response generated by closed loop pole at location A. Now we have to improve the steady state error without affecting the transient response. Students, now to improve the steady state error to 0, we will add a pure integrator or pole at origin, and with this the system type will be increased. Now the angular contribution of the open loop poles at point A is no longer 180 degree, and the root locus no longer passes through the point A as shown in the figure B. Now with this our system type is improved and steady state error is equal to 0, but the desired transients are no longer achieved because root locus no longer passes through the point A, which was our desired location for closed loop system poles. Students, now to solve this, we will add a 0 close to the origin in S-plane. Dear students, if you look at the figure, we have added a pole at origin to improve the steady state error, and we have added a 0 near to the origin. This 0 will again change the shape of root locus, and now from the figure you will observe that root locus again passes through our desired location A, where desired transients were achieved. The placing of compensator 0 will cancel out the angular contribution added by pole at origin or compensator pole. From the figure, the angular compensation added by the pole at origin is nearly equal to the angular compensation added by the 0. So their difference will be almost equal to 0, and the point A will be still the part of root locus, and the type of system is also improved, which makes the steady state error equal to 0. The gain required at a dominant pole is about the same as before the compensation, because the ratio of the length of compensator pole and compensator 0 is approximately unity. So we conclude that steady state error performance is improved without considerable effect on transient response. A compensator which consists of pole at origin and a 0 close to the pole is called ideal proportional integral compensator or PI compensator. Students, now in the given example, we will design a PI controller for a system to improve the steady state error. Students, the uncompensated system is given in figure A, which is operating with a damping ratio of 0.174. We have to show that integral compensator or system shown in the figure B reduces the steady state error to 0 for step input without much affecting the transient response. Second point is the compensating network is chosen with a pole at origin to increase the system type, and a 0 at minus 0.1, which is near to the origin, so that the angular contribution of the compensator evaluated at original dominant second order pole is approximately equal to 0. So the original dominant second order closed loop pole will still be on the new root locus. Dear students, we will start the solution by analyzing uncompensated system and will determine the location of dominant second order poles. Next we will find steady state error for the step input when the uncompensated network will be operating at damping ratio of 0.174. Students, after sketching the root locus of uncompensated system, we will draw a radial line of constant damping ratio for zeta equals 0.174, and the angle of radial line will be 100.02 degrees, and the point where root locus intersect the line of constant damping ratio will be the desired location of closed loop pole for a damping ratio of 0.174, and the location is equal to minus 0.694 plus minus j 3.926, and for this location of closed loop system poles, gain will be equal to 164.6. Dear students, now for the gain of 164.6, we will find out location of third closed loop pole, which is approximately equal to minus 11.61, and hence the higher order pole is much far away from the dominant pair of pole, so we have a better second order approximation. Now we will find steady state error constant. For the gain of 164.6, the static error position constant is equal to 8.23, and steady state error will be equal to 0.108. Now to make 0 the steady state error, we will add ideal integral compensator with a 0 at minus 0.1, which is shown in the figure. Now if you look at the figure, the third pole is at minus 11.55, which is again far away from the dominant pair of pole, so again we have a better second order approximation. Students, now if you compare the location of dominant pair of pole with the previous root locus, you will find a small difference in the location of dominant pair of poles, and the compensator 0 lies at minus 0.1, and the fourth pole of the closed loop system is at minus 0.09, which is nearly equal to the compensator 0 and will cause a pole 0 cancellation. Dear students, step responses for compensated and uncompensated networks are plotted in the figure. The step response of ideal integral compensated system approaches the unity in the steady state, while step response of uncompensated system approaches the final value of 0.892 in the steady state, which means that a constant or finite steady state error will exist between input and output. Dear students, another method of implementing proportional integral network is shown in the figure. In this type of implementation, sum of proportional error and integral error are forwarded to the plant. The compensating network which precedes G of S is ideal integral compensator and its relation is given by GC of S. Dear students, the ideal integral compensation with its pole on the origin requires an active integrator. And if we use passive networks, the pole and zeros are moved to the left close to the origin as shown in the figure. This placement of the pole although doesn't increase the type of the system, but it gives us improvement in the static error constant over an uncompensated system. Students, if we use active networks, we can place a pole at origin through which we can improve the type of the system and hence we have zero steady state error. But using passive networks, we can't place pole at origin and indeed it is placed near to the origin. And steady state error is improved with respect to that of uncompensated one. The figure represents compensator pole and zeros which are placed near to the origin and transfer function for the lag controller. Students, now we will demonstrate the improvement in steady state error for a system of type 1. If you look at figure A, we have a type 1 system and we have to improve its steady state error. Its static error velocity constant will be given by kV0 and will be equal to product of gains multiplied by zeros location divided by poles. Now if we assume that we have added a lag compensator whose transfer function was studied from last slide, now the new static error velocity constant will be given by Kvn and will be equal to gain k, product of zeros divided by product of poles, and this will be multiplied by compensator 0 over compensator pole. The compensated system is shown in the figure B. Students, now we will study the root locus of both compensated and uncompensated systems. The uncompensated system root locus is shown in the figure A. Now we assume a point P to be the location of dominant pair of pole. And after adding the lag compensator which adds pole and zeros together close to each other so that angular contribution of the compensator pole is nearly cancelled out by the angular compensation of the compensator 0. And the net angular contribution added up by the lag compensator to the point P is approximately 0 degrees. In figure B, a compensator has been added and point P is still approximately the same location on the compensated root locus. Students, after inserting the compensator, we find out that gain k is virtually the same for both compensated and uncompensated systems because the length of the vector drawn from the compensator pole and zeros are approximately equal, and all other vectors have not changed appreciably. Now we will study improvements in steady-state error. Since we established that gain k is same for both compensated and uncompensated networks, so if we relate the static error constant of both networks, we will come to result that static error constant of compensated network is equal to static error constant of uncompensated network multiplied by the ratio of compensator 0 over compensator pole, and it will be greater than static error constant of uncompensated system. Or we can say that improvement in static error constant of compensated system over the static error constant of uncompensated network is ratio of the magnitude of compensator 0 to the compensator pole. Now in order to keep the transient response unchanged, we know that compensator pole and 0 must be close to each other, and the only way the ratio of compensator 0 to pole can be large in order to give us appreciable improvement in steady-state error. And simultaneously, we have the compensator pole and 0 close to each other. Now to minimize the angular contribution is to place the compensator pole and 0 near to the origin. Dear students, in the given example, we have to improve the steady-state error by a factor of 10 if the system is operating with a damping ratio of 0.174. Students, the system is similar to the example of PI controller. Students, from G of S, the system is of type 0, and for step input it will have a finite steady-state error. From last example, the system operating at desired damping ratio of 0.174 have a steady-state error of 0.108, and static error position constant is equal to 8.23. Now the example required 10-fold improvement in the steady-state error, so our required steady-state error will be equal to 0.0108, and now corresponding to this error we will find static error position constant value from the relation of steady-state error. Now rearranging and solving for the position constant, we found that the value of static error position constant corresponding to steady-state error of 0.0108 equals 91. Dear students, now we know that in lag compensator, the steady-state error is improved by a factor, and this improvement corresponds to changes in the static error constant. Now the improvement in static error position constant for this case will be the ratio of static error constant from compensated to uncompensated one will be equal to the ratio of compensator 0 to compensator pole, or we can say that 91.59 divided by 8.23. The ratio of compensator 0 to compensator pole is equal to 11.13. Now if we choose the compensator pole at minus 0.01, we found that a compensator 0 will have a location of minus 0.111, and the transfer function of the compensator is represented in the figure. Now we will compare the compensated system with the uncompensated system by sketching the root locus for compensated one. Dear students, the figure represents root locus for the compensated system. In this root locus, we will draw a radial line which corresponds to damping ratio of 0.174. At this line, we will search for location where root locus intersect the radial line of constant damping ratio, and that will be our desired location for closed loop system poles. And this point of intersection is minus 0.678 plus minus j 3.836 with a gain of 158.1. The third pole of closed loop system is found at minus 11.55, which is far away from the dominant pair of pole, and fourth pole is found at minus 0.101, which is near to the compensator 0 at minus 0.111. The fourth pole of the compensated system cancels its zeros, and the third pole is far away from the dominant pair of pole. This leaves the remaining three closed loop pole of the compensated system very close in value to the three poles of uncompensated system, and hence the transient of both systems are approximately the same. Dear students, the figure represents the step response of compensated and uncompensated system, and the steady state error and the location of poles for compensated and uncompensated system are summarized in the table given. The steady state error for uncompensated system equals 0.108, where that of compensated system is 0.011. Now, if any of you have any questions, please ask.